Okay, this is a little experiment. I'm going to make a short video to complement the one Ben put up, and I am going to define non-deterministic time. Okay, here we go. So let me show the screen. All right, so recall that we determined in class, last time we met, we talked about time complexity for deterministic Turing machines, right? And this was approximately the number of steps in a worst case scenario for input of length n. So for example, right, saying that some Turing machine, some language L, right, was in a time class n squared means that there is a Turing machine which takes order O(n) squared steps for inputs of length n. All right. Now, it's actually pretty easy to talk about time complexity for deterministic algorithms, right? Deterministic algorithms, they take their input and we have these pictures, right? Deterministic. So a deterministic algorithm computes like this, right? And so asking how many steps it takes is just a matter of counting, let's call it like this, number of steps. Okay. So now if we have a non-deterministic algorithm, okay, then the picture is this branching, right? So the algorithm for a single input, right, we can have many different computational pathways, and some of them will end and others will keep going, right? And so maybe this is the full computational tree for some non-deterministic Turing machine. Okay, and I think reasonable people can talk about how to measure how many steps that is. Like maybe someone would want to count the total number of leaves. But we think of non-deterministic Turing machines as sort of running all these processes in parallel. And so the definition for non-deterministic time is the maximum number of steps in any one of these trees. So we think of the number of steps as the depth, and that's how we measure the time complexity. So let me formally sort of define this. So definition, okay, given n, an non-deterministic Turing machine, which is a decider, recall that we are only measuring the time complexity for machines that halt on every input. The time complexity of n is a function from the natural numbers to the natural numbers. That was true for deterministic ones. And it is defined to be the maximum number of steps n uses on any branch of its computational tree for any input w of length equal to n. So before we had that this was the max over any input, now it's the max over any input and any branch. Okay, so just to, draw a little picture, so we, this Fn, if we had an input of size n, right here, this Fn is referring to the depth. Okay, and so just like before with deterministic time, right, we can define time classes for languages. So let's define it like this. So before we had time, so now I'll write n time for non-deterministic time class. So n time tn is a class of languages L such that there exists a non-deterministic Turing machine n with time complexity order tn. So it's basically the same language, same definition as we had for time, but now we're just saying that there exists a non-deterministic Turing machine. And we defined the P, right? So recall that P, right, was the class of languages that can be decided in polynomial time. So this is languages such that there exists a Turing machine M such that the time complexity of M is order n to the k for some k, i.e. a polynomial time class. Okay, and so now we're going to define its counterpart, which is non-deterministic polynomial time. So NP is the class of languages L such that there exists a non-deterministic Turing machine N. I guess I should have said there exists a Turing machine L such that L of M is equal to L. And we should also point out that it's a decider. So let me add those facts, right? So there exists a non-deterministic Turing machine N, a decider, okay, with L of N is L, such that the time complexity of n is order n to the k for some k, a natural number. Okay. So we can, if you like, you can write that the non-deterministic polynomial time class is the union from k equals 0 to infinity of the non-deterministic time classes that correspond to nk. Okay, so a very simple generalization of deterministic polynomial time. Really, the only subtlety here is the fact that we should remember that when we're talking about the time complexity of a non-deterministic class, we're talking about the maximum depth of any computational tree, not the total number of steps aggregated over all the branches. Okay, that was a little experimental for me. I haven't tried recording these videos, and I haven't even used one of these pens very much, but it was fun to try. So we'll review some of this in class. See you next time.